Topic is fundamental concept of conductive heat transfer. Myself, Professor Radharani Dash, Dean and Professor of Department of Chemical Engineering, Haldia Institute of Technology. Regarding heat transfer, we know that three modes of heat transfer are there, basically conduction, convection, and the radiation. Conduction is the process by which heat is transferred from one point to another point without changing the position of the medium. So in this process, heat is conducted and dissipation of energy takes place from one atom to surrounding atoms when the atoms are in close proximity, such as in a solid. An example is that if we put a spoon in a cup of hot tea, the handle of the spoon becomes warm even though the handle itself is not in contact with the tea. Heat has been conducted from the tea to scoop and to the handle. Regarding convection, it is the mode of heat transfer which includes the movement of the molecules of the material, and it is only observed in the liquids and the gases. It is not possible in the solid because the molecule in the solid are tightly packed and are not free to move. Example of the convection is that if we heat water in a vessel on a stove, the water at the bottom is heated first, it rises to the top of, and the cooler water, which is more denser, down to the heated part, and this continues, heat is transferred throughout the fluid. In the radiation, it is a process for the energy emitted by one body travels in a straight line through a medium or through space. Radiation comes from the sun, nuclear reactor, microwave, ovens, radio antennas, X-ray machines, and the power lines. Today we are going to discuss about the heat transfer by the conduction in the solid. According to Fourier's law, the rate of heat flow across any surface must be proportional to the temperature gradient. And mathematically, it may be expressed as the dq by dA is equal to minus k into del T by del x, where q is the rate of heat flow, A is the area of the surface, T is temperature, and x is the distance measured normal to the surface. Here, negative sign reflects that heat flow occurs from the hot side to the cold side. In the steady state conduction, temperature of a body T is a function of the position only. It doesn't depend on the time, and the rate of heat flow at any point is constant. In unsteady state heat transfer, the temperature varies with both the location and the time. For example, if one end of a water-cooled wall is suddenly exposed to the hot furnace, say at about 700 degrees centigrade, as stated in this figure number 1, the temperature distribution curve, what is here given as the normal, that is that there is a no temperature gradient 25 to 25, but when it is exposed to the 700 degrees centigrade, the temperature distribution curve too will be decreased exponentially depending both on time and position, and it is unsteady state. But after a long time, the distribution curve 3 will not change the time, and it will be linear attending a steady state condition. So in this one-dimensional steady state condition, that is as per the Fourier's law, the equation 2 can be written as the q by A is equal to minus k into dt by dx, and the proportionality constant k of this equation is called the thermal conductivity, and units of the thermal conductivity k is calorie per hour meter degree centigrade. Thermal conductivity may be constant for the small range of the temperature, but for a wide range of temperature, it can usually be approximated as k is equal to A plus bt, where A and B both are constant. In unsteady state one-dimensional conduction equation, that equation can be expressed as dt by dt, which is proportional to the alpha. Alpha is equal to k by rho Cp, is called the thermal diffusivity, and unit of alpha is centimeter square per second. In the Cartesian coordinate, when the heat flows in the three-dimensional direction, then the associated conduction equation can be expressed as 1 by alpha dt by dt is equal to del 2t by del x2 plus del 2t by del y2 plus del 2t by del z2. Now, values of the thermal conductivity is higher in the metal, that is for the stainless steel the value is about 17 watt per meter degree centigrade. For the silver it is about 415 watt per meter degree centigrade. But for the porous glass materials, this value reduces to about 0.35 watt per meter degree centigrade, and for water the thermal conductivity value is about 0.5 to 0.7 watt per meter degree centigrade. For the gases the values is very poor and it is about 0.024 watt per meter degree centigrade. Thermometer with the gas is usually independent of the temperature, but it increases with the temperature because of the increase of molecular velocity, and solids having the low thermal conductivity are used as the insulator. Steady state conduction through a flat plate. Assuming that thermal conductivity K is independent of the temperature and area of the surface is very large compared to thickness. So in the steady state, there is neither heat accumulation nor depletion of the heat within the flat plate, and Q is constant along the path of flow. So from the Fourier's law, it can be written as the dt is equal to minus Q by Ka into dx. Integrating this equation within the limit t1 to t2 and x1 to x2, we get the equation Q by A, that is the heat transfer per unit area, heat flux, is equal to del T by del X by K, that is the del T by R. And R is called the thermal resistance of the plate. But when the resistance of the uses in series, that is for the composite wall, let the thickness of the layer be BA, BB and the BC for the three layers, and the conductivities of the materials of which are Ka, Kb and Kc. Also let the area of the compound wall be capital A, which is constant for the three walls, and delta Ta, delta Tb and the delta Tc be the temperature drops across the three layers A, B, C, and Ra, Rb and Rc are the resistance of the respective walls. Then delta T is the total temperature drop across the entire wall, can be given as the delta T is equal to delta Ta, delta Tb plus delta Tc. That is the summation of these three wall temperature drop. So rate of heat flow through the composite wall is given from the equation number 3, that is the Q by A is equal to delta T by R, and that can be expressed as the summation of QA BA by KA AA plus QB BB by KBA plus QC BC by KCA. Since Q is equal to QA is equal to QB is equal to QC, that is the heat flux normal to the surface area is constant here. Therefore, we can take the common Q instead of the QA, QB, QC. And the delta T can be expressed in terms of Q by A into Ra plus Rb plus Rc. That means the summation of the three resistance, which can be expressed as the capital R. Therefore, heat flux can be given by the equation number 4, that is the delta T, the total temperature drop divided by total resistance. So it is useful to recall the analogies between the flow of the heat and the electricity through a conductor. The rate of heat flow is given by the temperature drop per thermal resistance, and current flow is given by the potential drop by electrical resistance. If we consider the heat flow to the composite cylinder, at the steady state heat flow through a hollow cylinder of the length capital L with the inside and the outside radius Ri and Rho is given in the figure 3, and corresponding temperature of the Ri and Rho are the Ti and the Tu respectively. So considering a very thin cylinder concentric with the main cylinder of the radius R in between Ri and Rho, the thickness of the wall of this cylinder is dr, and if the dr is very small enough compared to the smaller, so Fourier's law can be applied as q is equal to minus k into dt by dr into 2 pi rl. That is the equation number 5. So rearranging the equation number 5 and integrating between the limits, it gives that q is equal to k into 2 pi l into ti minus to divided by ln of r minus ri. That is the equation number 6. Where logarithmic mean radius can be given as r ln is equal to r minus ri divided by ln of r by ri. And the logarithmic mean area of the cylindrical surface is given by ln, that is equal to 2 pi L into delta R divided by ln of R minus R by Ri. So heat flux at the steady state through cylinder body may be expressed as Q is equal to K into A ln into delta T by delta R. Similarly, if we consider the steady state heat conduction with the heat generation in the cylindrical body, so that can be considered that the steady state at the R is equal to capital R and T is equal to TO, we may find out the expression for the temperature as the function of the position and very easily. And the rate of heat input to the control volume, considering a thin layer in between the RO and the RI, that is the heat in into the control volume is given by the 2 pi L into R QR and R is equal to R, and rate of thermal energy out is equal to 2 pi L Q into R and R plus del R. And rate of heat generation should be 2 pi L into delta R into Q if the volumetric heat generation rate is the capital Q. So at the steady state condition, we know that heat in minus heat out plus heat generation is equal to 0. Therefore, summing up the three equations, we get the equation number 9. I am dividing the equation number 9 by the 2 pi r into A into delta, that is the unit volume. I am taking the limit delta r tends to 0. Integrating and rearranging the equation number 9, we can achieve the QR is equal to capital QR by 2, that is the equation number 10, which implies that heat flux is a function of the radial position. So applying the Fourier's equation in the basic equation number 2, and putting the boundary conditions R is equal to capital R and T is equal to T0, one can achieve this equation, that is the temperature profile. So T minus T0 is equal to QR by 4K into 1 minus R by R whole square. That is the equation number 11, and this equation of the parabola is the temperature profile, which implies the flux is proportional to the position. And since the maximum temperature at the core when smaller is equal to 0, then the T max minus T0 should be QR by 4K, just putting the smaller is equal to 0 in equation number 11. Average temperature calculation can be done with using this equation. When if we consider the total volume of the elemental section is the pi into capital R square into L rho Cp T average, and that will be the 0 to R and 2 pi R dr L rho Cp, function of the position, temperature is the function of the position, and using these equation we can calculate the T average. T average is equal to 2 pi R square 0 to R into T R dr. So putting this value, we can calculate the T max minus T0 divided by T average minus T0 is equal to 2. This is for the cylindrical surface. But when we consider the heat flow through the spherical body, then the equation should be changed and there should be the geometric mean area as convenient we have to use in space of the logarithmic mean area, and Q should be capital K into AGM delta T by delta R, where the AGM can be calculated as the 4 pi into RO into Ri to the power half. That is the root over of RO into Ri into 4 pi. So steady state heat conduction in the heat generation in the spherical body, we can find out the same procedure, the heating and the heat out, also the heat generation as per this equation, and we can achieve these equation is the heat in minus heat out plus the heat generation is equal to 0 as the cylindrical body, and dividing both sides by the 4 pi delta r, and the taking limit delta tends to 0, integrating in the rearranging this equation number 15, we can achieve the QR, the heat flow in a solid body, may be given as the Q into R by 3, which implies that heat flux is the function of the radial position. And applying the Fourier's equation and putting the boundary conditions as small r is equal to capital R, t is equal to t0, one can achieve this equation number 17, that is the t minus t0 is equal to q into r square by 6k into 1 minus r by r whole square. And this is the temperature profile in the spherical body, and the maximum temperature at the core when smaller is equal to 0. Then the equation 18 is T max minus T0 is equal to Q into R square by 6K. Here also, if we calculate the T average using this equation and the ratio of the maximum temperature by average temperature, we can get that the T max minus T0 by T average minus T0 is equal to 5 by 2. That's the equation number 30. Just similar way. Now heat loss to the insulated pipe and the concept of the critical insulation thickness. Here fluid is flowing at the 60 degrees centigrade, that means the inner temperature is the 60 degrees centigrade, and that is the insulation, and outer temperature is 21 degrees centigrade, that is the ambient temperature, and there is a flame coefficient on the outer surface is 11.35 watt per meter square. Here, considering the inner radius of the layer of insulation and corresponding temperature R, Ti at Ri, and the outer temperature is the To at Ro, and the convectivity transfer coefficient inside and the outside of the insulation is the Hi and Ho. Conductivity of the insulating material is the Kc. The assuming Hi, the inside heat transfer coefficient is very large compared to the HO, outside heat transfer coefficient. So effect of the conductive heat transfer on the critical insulation thickness is very important here. Here, two opposite factors come into play on the rate of the heat transfer when the insulation thickness on a pipe increases, because there are two major resistance act in the series. One is for the layer of insulation and other is offered by the gas film on the outside. With the increase of the insulation thickness, surface area increases, so which increases the loss of heat due to the convective heat transfer. But in the other side, conductive heat transfer decreases with the insulation of with the insulation thickness. So as a result, overall heat loss increases fast, reaches a maximum at the critical insulation thickness, and then it decreases. And it shows in the next slide, that is the relation between the heat loss and the insulation thickness. If we increase the outer insulation thickness, at first the heat transfer increases and reaches a maximum point, and then it decreases gradually. So calculation of the critical insulation thickness can be found out using this equation, where the capital Q is the rate of heat flow and delta T is the difference of the temperature inside and the outside, and at the denominator there is a three part. One is for the inner heat transfer coefficient, other is the outer heat transfer coefficient, and middle term is the for the conduction. But since HI is too high compared to the HO, first term may be ignored and the expression should be reduced with the second line. And if we differentiate the Q with respect to RO and it puts at the is equal to 0, then we can get the RC, that is the critical radius, which is here that is given by the Kc by HO. Kc is the conductivity of the insulation and HO is the outer film coefficient. If the second order derivative d2q by dRO2 is a negative, it confirms the conduction for the maximum rate of heat transfer. And the value of the RO minus RC is called the critical insulation thickness. And when the insulation is applied on the steel pipe, its thickness should be above the critical value to check the maximum heat loss. However, for insulated electrical wire, the insulation thickness should be very near of the critical radius so that the heat loss is the maximum. And when the value of the RO minus RC becomes negative, it means that the critical insulation thickness does not exist for this case. This is the problem on the thickness calculation. The problem is the wall of the refrigerator container mounted on the tank consists of 1.5 mm of the steel sheet outside and 3 mm plywood inside, when a layer of glass wool insulation between. The container is being designed to maintain the inside temperature of the minus 10 degrees centigrade while the outside temperature of the 25 degrees centigrade. So what should be the thickness of the glass wool layer to limit the heat loss to 6 kilocalorie per hour per meter square? If the thermal conductivity of the steel, plywood and the glass wool are given as 38.0, 0.09 and 0.025 kilocalorie per hour per degree centigrade. So we have to first assume the thickness of the glass wool is X and we have to find out the resistance, individual resistance, and summation of the resistance should be R1 plus R2 plus R3, and from that we know that the Q by A is equal to 6 into kilocalorie per hour per meter square. From this equation, very easily we can calculate the small x, the thickness of the glass wool. And the next problem is on the to find out the values of the junction temperature between the two layers of the insulation. The procedure is we have to find out the resistance offered by the individual insulation, say RA and the RB, then summing the total capital R, that is the total resistance offered by the two insulation can be found out, and the rate of heat loss from a certain value of the pipe we can find out the delta T by the R, and let the junction temperature, if we consider the small T1, then the outer surface temperature minus T1 is equal to delta T by R into RA. And from these we can find out T1, the junction temperature, very easily. And next problem is very easy, that is to find out the RC, and all the data they are giving. We know the HO, we know the Kc, and so applying these values we can find out the RC very easily. Kc by HO is equal to 37.8 millimeter, and the critical insulation thickness should be RO minus Ri, that is the 35.2 millimeter. So these are the total discussions on the reference books of the unit operation of the chemical engineering by McCabe and Smith, process heat transfer by the DQ Kern, and the heat transfer principle and application by Professor B.K. Dotto. Thank you for your patience.